In Eastern Europe, a small commercial quadcopter crosses the front line. Within 5 to 10 kilometers of the nearest electronic warfare emitter, its GPS receiver loses lock. Stabilization fails. The drone enters fail-safe and either descends or, more often, simply hovers in place, becoming a stationary target. This white paper makes one claim: a drone that depends on satellites for stability is not autonomous. It is automated within a permissive environment. When that environment becomes contested by jamming, by signal multipath, by a tunnel sealing, the system fails and a $50,000 asset becomes a paperweight. True autonomy means perceiving, deciding, and acting without an external tether. That capability lives onboard or it does not exist. Begin with the physics. GPS satellites orbit roughly 20,000 kilometers above the Earth. The signal arriving at the surface is comparable to a 25-watt light bulb seen from 10,000 miles away. A ground-based jammer drawing only 10 to 40 watts can create a blackout zone several kilometers wide. Inside that zone, the signal-to-noise ratio collapses below the receiver's tracking threshold. The cloud is no escape, at 20 meters per second. A 300-millisecond cloud round-trip translates to 6 meters of blind flight. Above 700 milliseconds, teleoperation becomes uncontrollable, and the radio uplink itself is a high-power beacon, easily triangulated by enemy direction-finding assets. The remedy is Visual-Inertial Odometry, VIO, fused with onboard semantic intelligence. The architecture builds in 4 stages. Stage 1, the inertial measurement unit. Accelerometers and gyroscopes report at 200 Hz to 1 kHz. They are fast, but they drift. Position is the double integral of acceleration. Any small reading error grows quadratically over time. A consumer-grade IMU can drift by meters within seconds. Stage 2, the camera running at 30 to 60 Hz tracks distinctive features across frames. Slower but anchored to the world. Both streams enter a sliding window factor graph, the back end of ORB-SLAM-3. Each new measurement relinearizes recent poses. The drift estimate gets corrected as evidence accrues. Stage 3, replace the classical feature detector with a deep front end, superpoint, and superglue. For standard ORB feature matching fails in low light or under motion blur, learned descriptors keep tracking alive. This is the difference between a benchmark demo and a tactical drone. Stage 4, semantic masking. A real-time segmentation network, SegNet, or a YOLO-class detector labels every pixel as static or dynamic. Trucks, foliage, people are masked out of the VIO optimization. The drone tracks only what does not move, and loop closure. Using bag of visual words descriptors, recognizes previously visited locations and snaps the entire trajectory back into alignment. The result is a closed system. No satellites, no cloud, drift rates of 1 to 2% of distance traveled, in environments where GPS simply does not exist. The hardware reality is the NVIDIA Jetson Orin family. The Orin Nano runs 40 trillion operations per second in a 7 to 15 watt envelope, entry-level VIO. The Orin NX delivers 100 trillion operations per second, with 16 gigabytes of memory, in a 10 to 25 watt envelope, the optimal balance for tactical micro-drones and industrial inspectors. The GX Orin reaches 275 trillion operations per second for heavy industrial roles. Software fits the silicon. TensorRT compiles the neural networks. 8-bit integer quantization doubles or triples inference throughput. Vision programming interface accelerators handle feature tracking. CUDA kernels parallelize the bundle adjustment. The flight controller receives odometry updates at 50 Hz or higher, fast enough to close the stability loop. Real-world consequences. In oil and gas, a single pipeline failure costs around $8.5 million to remediate, the repair itself around $75,000. VIO lets a drone hold station beneath a bridge or inside a tank farm where GPS multipath would push it into the structure. In mining, a 30-minute drone flight replaces days of manual surveying. 2 architectures. The wrapper drone needs satellites overhead, a cloud back-end, and a radio link wide open. In a contested environment, all 3 fail, and a hovering drone is a stationary target. The engine drone fuses sensors at the edge. It perceives, decides, and acts in radio silence. The asymmetry has a price tag. The NIST-sponsored study estimated GPS contributed roughly $1.4 trillion to the U.S. private sector between 1984 and 2017. Losing the service costs roughly $1 billion per day. A 40-watt jammer can take down a $50,000 asset until the asset stops needing the satellite. The full architecture sits in the 18-page brief. We named it the Autonomy Paradox, engineering resilient navigation in GNSS-denied and contested environments.